Assalamualaikum warahmatullahi wabarakatuh all. We are now in a new topic. It is exponential and logarithmic functions. Before we start the new topic, let me remind you so that you always remember that exponential functions is not the same as exponent itself. Exponent is very broad idea, but exponential functions is when you have in your mathematical functions, the variable itself is an exponent. Okay, let's look at a very simple exponential function. Now, the simplest exponential function that we can think of is this. So let's say y as a function of t, specifically we can write it this way, equals to b to the power of t, such that b has to be greater than 1. So this is our exponential function. As you can see here, y depends on t. So we have two variables here, y and t. Y is the dependent variable because it depends on t. Nevertheless, t is an independent variable because it doesn't depend on anything in the system or in the function. But you can see here, t becomes an exponent to the base here. So when I say base, b is actually a fixed number and it is a base of the exponent of t here. So for instance, we can have b equals to 2, b equals to 3 and whatnot. Now you look here, we have imposed restriction to this equation, specifically b greater than 1. Okay, let's say no restriction is imposed on this function. Then you can see the exponent here, the t, can be any real number including negative value, isn't it? Okay, so when t can include negative value, what does it mean here? This implies that the domain of this equation is actually all real numbers. Okay, now let's put aside t. We want to talk about b. Okay, so here, why do we need to put restriction such that b has to be greater than 1? Okay, can we have b less than 1? Can we have b negative value? Okay, can we put restriction instead of b greater than 1? Can we have b greater than 0? Okay, all right, is it yes or no? Okay, so for instance, let's say I pick b, can be any real number, includes negative value, and t can include can include any real number. Okay, so let's say b here is equivalent to -2, and let's say t here is equivalent to let's say half. Okay, 1/2. All right, so that means y equals to -2 to the power of 1/2. Okay, this can be rewritten as -2 square root, isn't it? Is it possible for us to get the solution of square root of -2? It's not possible. That is why we need to put restriction on b. Okay, if this happens, then we get what we call irrational number. The next thing that we want to look at is how does exponential function look like in the form of graph. So let's look at it in this frame of diagram. So let's say we put y on the vertical axis and then t on the horizontal axis, and remember this is not yx anymore, because y is a function of t. Okay, let's say we have a specific exponential function. Let me write it here, y as a function of t, but we want to make it more specific. Okay, so bt in it, but even more specific by putting numbers. So we have y equals to 2 to the power of t. Okay, and you see the base here is 2, which is greater than 1. Okay, so let's say we have this frame of diagram. What we want to do here is that to plot the graph such that we have t between -3 up to 3, for instance. Okay, actually with this kind of mathematical expression, we don't need to plot it one by one, but for the time being, we just do simplest way to draw a graph. Later, like I said to you previously in previous chapter, there's a way to graph a model by looking at the slope, by looking at the existence of intercepts, and also by looking at the linearity or convexity of the graph. Okay, now, so here, just imagine if we have t minus 3, minus 2, minus 1, 0, okay, and then what happens here is 1, 2, 3, try to find y values, okay. Obviously, when t is 0, okay, then y equals to 2 to the power of 0, then it becomes 1 here, isn't it? Okay, if t is 3, then this one becomes 8, isn't it? Okay, try to figure out the rest of the answer, okay, because this one is very simple actually. Okay, so here 0 is here, let's say 1 is here, okay, if it is 2 to the power of 2, it becomes a 4 in it. Okay, so we have 1 here, 2 here, 3 here, right? 1 here, 0, 1, okay, and then we have, 1, 2, for instance, and then we have 2, 3, 4, 4, for instance, and then we have 1 here, 5, 6, 7, 8, somewhere here, 8 here. We don't have enough space here, so you draw accordingly, and then here you can join all the points. Okay, then you can have something like this. Okay, so this is y equivalent to 2 to the power of t, something like this. So what is this actually? This is basically hyperbolic function in it. Okay, so this is plotting, and actually, like I said earlier, there's a simpler way to do it so that we can get nice graph. If we draw it nicely, it should be like this, yeah. Okay, all right, now if you look at the graph that has been plotted just now, okay, can we figure out some, very important or salient or distinct features of this exponential curve? So this is exponential curve. As you can see, when we draw it, the first thing that you can recognize is that it is continuous. When I draw, did you see when I draw just now, it is continuous, okay? From one point to one point, there is no gap when I drew it just now, isn't it? So it's very smooth, a very smooth drawing. So if it is continuous, the curve is continuous and smooth everywhere along the line, along the points. So what's the implication of this continuity in mathematics? The implication of this continuity is that this function can actually be differentiated. We can do differentiation. Okay, that's the first thing. And the second thing, when I drew it just now, can you see when I drew it, there is no any point in when I drew it, okay, leads to the downsloping, drawing, isn't it? So it keeps increasing from one point to another point. It keeps increasing monotonically, okay? So it is monotonically increasing, monotone, okay? And as you can see, as you increase t, y keeps increasing, drastically. In mathematical terms, y increases at increasing rate for all t. Okay? Now, if this is the case, what are the implications of this on the first and second derivative of this equation here? Okay? Derivative means what? Results of differentiation. The first derivative is you differentiate it the first time. You get the results. That result is what we call first derivative. The second derivative is you differentiate it second time. you get the result is second derivative. So if that is the case, if it is monotonically increasing, what's the implication on the first and the second derivative of this function? The first derivative shows that if y is increasing as t increases, that means this function is upsloping in it. Okay? The first derivative shows us slope in it. Okay? The slope is increasing. And now, I did mention to you just now, when it is monotonically increasing, as y increases at increasing rate for all x. Okay, so here, y increases at increasing rate for all x, or for all t, specifically because we use t here. So it means, as t increases, the increase in additional y becomes larger and larger. Here, from 1 to, from 1 to 2y, the additional increase is 1y only. From 2 to 4y, the additional increase is 2. From 4 to 8 here, when t increases by 1 unit again, then it becomes what? 4. Can you see? The additional y becomes larger and larger. That is why we say it is monotonically increasing. So the second implication is that it has implications on second derivative. The second derivative will be positive because the slope is increasing at increasing rate. That's what it means. We'll study more about this in the later chapter, but at least I give you, some basic idea about the monotonically increasing function. Okay, so these are the terms that are frequently used in the study of mathematics. Yeah. Okay, now the next thing that we want to look at when we draw the graph we want to analyze is that if you see here, I did mention to you when we plot, we need to plot it within this range, -3 up to 3. We can also extend it to, let's say, -10 and whatnot, but because I just want simply to, to save the space here, so I request you to draw between -3 and 3. So here, the t here, remember all t values, permissible t values are what we call domain, isn't it? So the domain of the function is here, you can see from negative to positive number. But then, as you can see, even if we extend the domain to, another negative number, when you extend it, you can see it's, becomes flatter and flatter, but it never touches the horizontal axis. Okay, so y value here, regardless the t value, whether it's negative or positive, y values here, okay, is basically is an open interval between 0 and infinity. Okay, so that's another thing that we can see from this graph. Now, another thing about exponential function is that if there is an exponential function, that exponential function must have its inverse function. So if we have exponential function, what is the inverse of exponential function? The inverse of exponential function is logarithmic function. Okay, now another thing that we need to, emphasize is that, okay, we can express any positive value as a unique power of a base. Okay, and remember the base here is b, and we restrict the base with certain restriction, that is b greater than 1. Okay, now my main point here is that if a positive y can be expressed as powers of various alternative bases, then that means there must exist a general procedure of base conversion. Okay, So it means we must have general procedure of base conversion. If you don't get me, let's look at the numerical examples to explain this point. Okay, so let's say we have this example, yeah? Here, we have expression 2. In particular, y equals to 4 to the power of t. The base is 4, the power is t, y depends on t. Because t becomes exponent, then this is what we call exponential function. And actually, we can rewrite expression into as 3. Why? Because when we have y equivalent to 4 to the power of t, this implies y is actually equals to, you look for 4 here is actually 2 to the power of 2, isn't it? 2 square. Okay, to the power of t. And this implies what? This implies y equals to 2 to the power of 2t. In it, it's 2 times t. Okay. All right. Now here, can we say that equation 2 is actually equals to equation 3? Now let me emphasize you one more thing. Perhaps some of you might be getting confused if I write it this way. Let me write it properly. This one is actually this. This. 2 to the power of 2 times power of t. That's the correct one, so that you won't be confused. So can we say that equations 2 here is actually equals to equation 3? Okay. If you look at equation 2 here, the base is 4 and the exponent is t. But if you look at expression 3 here, the base is 2, but the exponent now becomes 2t. Isn't it? In 3 here, we can clearly see that the exponent has been changed from t to 2t, isn't it? Also in 3 here, we can also see that the base is changed from 4 to 2. Okay? Although the base and the exponent has changed, but actually 2 and 3 are just the same thing. Now, as you can see here, if this is the case, then there must be, okay, a general procedure of base conversion, isn't it? Because here you can see we can change the the base, or convert the base from 4 to 2. Okay, let me rewrite again expression 2 here. Y equals to 4 to the power of t. This is expression 2. And then we have expression 3. Y equals to 2 to the power of 2t. This is expression 3. All right. Now let's say let q equals to 2t. What can you see here? Q equals to 2t. That means this one equals to q, isn't it? Then substitute q equals to 2t into 3. Now this yields what? This yield, okay, y equals to 2q, in it. Okay, y equals to 2q. So in this case, when we write it, y equals to 2q, isn't it similar to equation 1? Equation 1, if you can recall back, it is y equals to, b to the power of t. And then in this case, it is a function of t, not b, such that b must be greater than 1. So this is equation 1 that you have seen earlier. Okay, isn't it the same, isn't it? Therefore, look at expression 3 here. If we try to generalize equation 3, that means we can also have the following. Generalize equation 3, then we can have the following. Y as a function of t, I use g so that I can differentiate function 1 and the next function, yeah? I use g instead of f. Okay. Y as a function of t then can be rewritten as b to the power of 2t in it. I call this expression 4. Okay, can you see clearly? Okay. Now, let's look at this graphically. Why? Because if we write it differently like this, although they have, the same meaning, because 2 is actually the same as 3, but if we write it differently, the way written here is not the same as the way written here, isn't it? It can give us two different curves. Why this happens? Okay. So let's look in the form of graph. There's a concept behind this, yeah? So like I said earlier, we have y equals to 4t. This one is actually in generic form is y equals to b to the power of t. 4 to the power of t is equals to b to the power of t in generic form. Likewise, we also have y equals to 2 to the power of 2t. In generic form, we can have what we call y equals to b to the power of 2t in it. Okay. As you can see here, the exponent here is twice as the exponent here, isn't it? Now let's try to put all of this concept in the form of graph. Forget about all of this. Now let's use this. Y equals to b to the power of t, and then the next one, y equals to b to the power of 2t. Okay. Let's say we have the same base value. Okay, for these two, the base here is the same as base here, b. Yeah, I'm referring to b. And you can see here the exponent in the second one is double the exponent in the first one. But then we must remember y here must be equal to y here. The value of y here must be equal to the value of y here. Okay, because otherwise we cannot explain this concept. So let's say we need to have the same value of y. Call that y naught. Okay, all right. So in the form of graph here, let's say we have y here, we have t here. I'm gonna draw this and this in the form of graph. Okay. So if t is 0, then y is 0, isn't it simple? Okay. But for y equals to b to the power of 2t, if you draw it, then you get something like this. Okay. Let me draw it properly, because something is wrong here. Okay. If we draw the first one here, then it still have the same thing, but then the drawing is much flatter. Okay, so the first one here is y as a function of t, but then b to the power of 2t. The next one here, the flatter one, y, okay, as a function of t, but then is equivalent to b to the power of. Now let me fix a little bit, because otherwise you get confused when you read the textbook. We have two different functions here. The way we wrote it, y equals to b to the power of 2t, I wrote function of tf, isn't it? Now let's change it to gt, and then this one to ft, so that when you read the textbook, you can always refer to the textbook when you don't understand anything in my in this video. Okay, anyway, so here we have two different functions. One function here, the first one here, I'm referring to this. Okay, y equals to y equals to b to the power of 2t, okay, as a function of t, okay. So if you see the exponent here is twice as the exponent in this function. I mean, the exponent here is twice as the exponent of the flatter function, okay. So because of that, and also let's say we adopt the same base, okay, let's say we adopt the same base. If you can recall back last time, okay, the same base is 2, for instance. Let's say the same base, okay, or whatever number, okay. This is just a general explanation, yeah, so I'm not using number to explain, okay. And since the identical base is adopted for the two functions here, okay, then let's say we assign an arbitrary value of t for the first function here, okay. Arbitrary value of t for the first function is t naught, okay. And then let's say we assign arbitrary function of the, for the second function here, which is 2t naught for function ft here, okay. Then these two value of t, okay, t naught and 2t naught, must yield the same value of y. Now in this case, when it is t naught, the value of y is y naught. Now in this case also for the flatter function, when the value of t is 2t naught, okay, the value of y is the same, y naught, isn't it? Okay, so specifically what I'm trying to say is f2t naught, isn't it, is actually the same as gt naught, isn't it? Okay, and this is actually the same as what? As b2t naught, isn't it? Okay, and this is also the same as y naught. Okay, right. Now at y naught, if I draw the dash line like this, yeah, horizontal dash line, and then it passes through, gt and also ft, then here for this point, let's say I label it as a j, and this point, let's say I label it as k, okay. So you can see here the distance of y naught j is actually half of the distance of y naught k, or in other words, the distance of y naught k is double the distance of y naught j, isn't it? And here what we can say is that doubling the exponent actually has the effect of compressing the exponential curve halfway towards the y-axis. As you can see, in this function, the exponent is double. In this function, the exponent is not double. Okay, this is half of the double here. When we double the exponent, what happens here is that the curve is compressed halfway toward the vertical axis. Okay, you can see here the distance is halfway toward the vertical axis. This one is double towards the vertical axis. Can you see? So again, I repeat, by doubling the exponent, the effect is the curve is compressed halfway toward the vertical axis. But if you halve the exponent, if we try to make the exponent becomes half of this one is double, we half it, it becomes this, isn't it? Okay, so halving the exponent actually extends the curve away from the vertical axis by how much? Okay, by twice the horizontal distance. Okay, so we are talking about the distance, horizontal distance, how far it is from the vertical axis. That's what I mean. So if you double the exponent, the horizontal distance is, half toward the vertical axis from the flatter curve here. But if you reduce the exponent by half, okay, from here to here, then you can see the horizontal distance is doubled away from the vertical axis, isn't it? By the horizontal distance, the distance is twice. Okay, all right, so I hope it is clear here. Now the comparison here is made horizontally. Can you try to make the comparison vertically? Here we have the same y naught, isn't it? So if you try to do it vertically by comparing the distance vertically, then we are looking this way, isn't it? The distance, how much here, okay? Then it means you must have the same t for the analysis. Let's say you pick this t, that means the y from here to here. What happens to the y value? Okay, if if you double the exponent, what happens to the y value? Okay, that is the case of doubling the exponent. What if the exponent is the same, but we double the base? What would happen to the curve here? Change in exponent, and we can see that doubling the exponent has made the curve nearer by half toward the vertical axis. What if the change is the base instead? Okay. Why don't you try to modify the base by doubling it? So you need to analyze it vertically. Okay. Now, so if you have these two different types of modification, modify the exponents or modify the base, what would happen is that we can actually generalize equation 1. Recall back, equation 1 is actually y equals to b to the power of t, isn't it? Now, if we talk about the base here, b must be multiplied by something, isn't it? Let's call it a. So, if we can modify the base, or we can modify the exponent, then we can generalize equation 1 here as 5. As you can see, 5 is actually y equals to a times b to the power of c times t. Okay? So we see the coefficient of a, and then we see c here. Alright, both of them are basically a constant. And the question is, what happens if a and c are positive? What happens if both of them are negative? Okay. Now, what are a and c? Until you do the exercises that I mentioned to you on the, doubling or halving the base, then you can clearly understand what I'm going to say now. A and C are actually agents. What kind of agents? A and C are compressing or extending agent for this function. Okay, so if you can see, let's go back to doubling the exponent case. When you double the exponent, you are basically compressing the curve, isn't it? But if you make the exponent half from the double, you are actually extending the curve, isn't it? But what about the base? If you double it, what happens? Okay, If you double this a, what happens? So please do the exercise, read the textbook, then you can get what I mean. Okay, now we are done with, this kind of concept, and this concept is very important, yeah, because it gives you some idea about drawing graph and the behavior of graph, and the function. So you can have many different types of exponential functions with different types of base, okay, but some bases are preferred over the others. And why? Especially if the base is irrational number denoted as a, and e, I'm sure you have seen this in your high school, and e is actually 2.71828 blah 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 blah. Okay, it doesn't stop, so it is an irrational number. What does it mean by irrational number in this case? It's very obvious that you cannot come up with a fraction. Okay, when you try to come up with a fraction, the decimal point here, the number after the decimal point doesn't stop. Okay, so what's the example that we can think of? So here are the example. Y equals to e to the power of t. Y equals to e to the power of 3t. Y equals to a times e to the power of rt. Okay, isn't it the same as y equals to a to the power of b times ct, isn't it? So capital A here refers to this, r here refers to this, isn't it? Okay, but anyway, and another way to write this function is actually this one can be rewritten as this one can be rewritten as this one can be rewritten as this. All right, now again, let's go back to this question. Why this base is preferred over the others? What's so good about e? So let's say we look at this expression. Can you try to find the derivative of y equals to e to the power of t? If we have y equals to e to the power of t, when we want to find the derivative here, is equivalent to what? E to the power of t. Can you see? The work of differentiation is so simple that you don't even have to do anything except to rewrite again the equation, isn't it? What if we want to differentiate this? So let's say y equals to e to the power of rt. Now let's say w is equivalent to rt. So we can rewrite, this one as y equivalent to e times e to the power of w. Let's differentiate it with respect to t, because t is the variable, the independent variable in this case, isn't it? That give effect on the dependent variable, which is y. So how to differentiate it? Let's use a chain rule. If you use chain rule, so dy over dw and then dw over dt, isn't it? Because in w itself we have t, and we want to differentiate this function with respect to t. So because w consists t, so we differentiate w first and then we differentiate t. So what do we get? So a, all right, e, w, and then in w we have t, then we differentiate rt, it becomes r here, isn't it? But because we know w is rt, then we make it more specific, equals to a ert times r. So that's the answer. Okay, so we are using chain rule. We call back the differentiation rule that you have learned in first year. Okay, so can you see that the differentiation process is very easy for these specific types of base? That's why this base e is, used a lot in mathematics, especially in economics, mathematical economics, to explain the certain concept, especially growth concept. We want to look at the economic interpretation of natural number e. So if we try to put in the form of mathematics, actually number e is the limit expression. Okay, so e has its limit expression as this, as the one in 8. E is actually the limit of function n, okay, as n approaches infinity, such that function n, okay, can be described as this: 1 plus 1 over n to the power of n. So e is actually specifically the limit of 1 plus 1 over n to the power of n as n approaches infinity. Okay, so how can we use this kind of, limit expression of e, okay, in the economic study? The very famous use of e in economic study is the in the process of interest compounding. So let's say interest rate here is 100% for simplicity, okay, and then let's say we want to compound within a year, okay. So here, and let's say initial value that we have for money is 1 quid. All right, so initial value here refers to initial principal. So here, if we compound within a year, then we can have V1 equals to 1 pound times 1 plus 100%. 100% is 1, isn't it? So to the power of 1. So what do we get? Get 2 pound. Okay, that's what we get. Now just imagine we still have money 1 quid. Interest rate is 100%, and this is actually annual interest rate, yeah, before I forget. But then we want to keep the money within 1 year, but then we want to compound it twice per year. So this is what we call compound semi-annually. When we compound semi-annually, we compound it twice a year. That means the annual interest rate here has to be divided into 2. It becomes 50%, isn't it? Because for the first 6 months, interest rate 50% is compounded, and then for the next 6 months, another 50%. Okay, so what would happen here? Okay, so here, so if we have 1 year, compound once, then it becomes 2, isn't it? But if we compound it twice per year, but the initial, the initial principal value is still 1, so 1 plus 1 half 50%, and this one 2, isn't it? Okay, so what is the answer? 2.25. Let's say we want to compound it instead of 2, we want to compound it 3 times. 3, 1, 1 plus 1 over 3, 3. What do we have here? Is 2.37, is 037, 037. And if we compound it 4 times a year, okay, but we still keep money 1 year. Okay, 1 over 1 plus 1 times 1 plus 1 over 4 to the power 4. Then we get 2.441, 40625. Okay, and so on and so forth. Let's say instead of compounding it 4 times per year, we compound it every single point of time. Or in other words, we compound the interest rate continuously during 1 year without stop, without, non-stop. So the number of compounding in this case becomes infinity, isn't it? Because we keep compounding it. And you look at the pattern of the number here. When we compound it, increase the number of compound. Can you see what happens to the value? It increases from 2 to 2.5, and then increases here, increases further, isn't it? So if we compound it in infinite amount, then we can see that the value here, the answer here, okay, will reach to the value of E, isn't it? Okay. I recall back what is E. E equals to what? E equals to 2.7 something. Okay, so that's what we can see. So the results here approaches E. And we know that the value of E is a natural number. Okay, so that's why it's very useful to use E in the study of economics when it comes to compounding. Now, what else can we use? What else is the use of E here? Here we can see the growth in money. Okay, and other types of use here is to calculate the growth of population. Okay, in these in the economic example that I've mentioned to you just now, you can use it to calculate the growth of saving. Okay, now in this case, E is actually one. It's actually 2.71828 blah blah blah. It's actually the value at the end of the years. So if you have one quid, okay, you keep it for 1 year, but then interest rate is compounded continuously in the bank, okay, then the value that you receive at the end of the year after you save in the bank is this. Okay, so the value of principal has grown from 1 quid to almost 3 quids, isn't it? So here you keep 1 quid for 1 year with 100% interest rate, compounded continuously. 100% interest rate is interest rate, annual interest rate, but then you compound it continuously. So you get 2.718 quid, okay, 1828 quid at the end of the year. All right, now just imagine if we keep money in the bank and the interest rate is compounded every single second. Everybody wants to put money in the bank. They don't want to consume, isn't it? Because the value has increased by more than double. Isn't it interesting and attractive? Isn't it? But then another question is, what happens to the effective interest rate in this case? We know that the annual interest rate is 100%. But after compounded continuously, what is the effective interest rate value? Can you figure it out? Okay, so like I said earlier, E, or natural number here, is not only used to calculate the growth of, saving after you compound the interest rate, but in other types of field, especially in biology, they want to calculate the growth rate of, population of certain animals, certain plant, and whatnot. So there are a lot of use of E. That's why it's very useful. And it is very easy to deal with E as a base, okay, of any exponential function compared to other base. When we talk about growth, when we talk about, increase and whatnot. So E, or natural number here, is widely used in any kind of application, be it economics, biology, science, or whatever. Okay, now we have done the specific example here. In general, when we try to, let's go back to this example, yeah? In general, when we compound interest rate, within a year continuously, then we can have a specific, generic function for this. And the specific generic function for this is given by this. So here, if we see expression 11, it is actually the general form of what we have done earlier. Right, if you see the formula here, Vm equals to A, and then in bracket 1 plus R over M, and then to the power of MT. Okay, so A is the initial principal, let's say 1 quid. Okay, T is the investment year. In our case, previously is 1 year. R is the nominal annual interest rate. In our case is 100. And what about M here? M here is how many times we compound the interest rate for each year. Okay, so now we try to relate expression 11 with this function. Okay, so actually expression 11 can be rewritten as follows. So if you see here, this is an alternative form of the previous expression. So Vm is A, and then in the square bracket, we have 1 plus R over M, and then, close the circle bracket, you have M over R, and then the whole thing to the power of RT except A. So here, I want to specify to you, if we have MT initially in expression 11, how it becomes, like this. Because we have, M over R times T, cancel, we can get back MT, isn't it? Okay, now, so let's say, let W equals to M over R, then we substitute it back into expression 12 here. So we can have, you see here, R over M is actually the inverse of W, isn't it? So we can have 1 over W here, and then W here because M over R. Okay, and then the whole thing here in square bracket to the power of RT. So the main point here is to see what happens to the whole function here, function 12, if variable W, okay, and also M changes. So here, let's say M, recall back, M is the number of compounding, how many times we compound interest in a year. So let's say as we compound interest rate continuously, infinite amount, non-stop, not just once, not just twice a year, not just 4 times a year, then what happens to W here? If this one becomes infinity, approaches infinity, the whole thing will increase, isn't it? And increase, and W will approach infinity as well, isn't it? And then another thing that we need to look here is that as M approaches infinity, we know that in between here, W also approaches infinity. So when W here approaches infinity, what happens to the whole thing here in the bracket? Okay, what happens to the whole thing in the whole bracket here? Then the whole value here will approach E, isn't it? The whole bracket here will approach E. Okay, so in general, we can rewrite it this way. As M approaches infinity, then we know that W will approach infinity as well. Then the whole value in the bracket here will approach E. Okay, so that's what it means here. So we have V equals to limit of V as M approaches infinity is actually equivalent to this. So here, let's go back to this. So the whole thing here, okay, will be the same as E. Okay, will approach E actually. But then, okay, let me rewrite again before we continue analyzing the expression. Let me rewrite again expression 11 here. Vm equals to A 1 plus 1 plus R over M to the power of MT. This is expression 11. Now, what's the differences between equation 11 here and also 13? Okay, if we look at 11 here, T is actually a discrete variable. Remember the T is actually time, let's say per year, okay, period of, of saving, for instance. Okay, so it is a discrete variable. Just imagine the number of times we compound, which is M, okay, M equals to 4. Okay, then what happens to the value of T? The value of T can only take values that are integral multiples of 1 over M, isn't it? Okay, so for instance, if M is 4, then T can be 1/4, or 2 over 4, or 1/2, or 3 over 4, or maximum 1, isn't it? Because 1 year. Okay. Now, but then if let's say M is equivalent to 6, okay, recall back, yeah, because T is a discrete variable, time is a discrete variable, then again I repeat, it can only take values that are integral multiples of 1 over M or reciprocal of M. So in this case, if M is 6, then T can only take value of 1/6, 2 over 6 or 1/3, 3 over 6 or 1/2, and then what else? 4 over 6 or 2/3, and then 5 over 6, and then total 1, isn't it? Okay, but then just imagine as we increase the number of m here, and then m becomes too large and m approaches infinity. Okay, so now we are talking about 13 as m is too large and m approaches infinity, then 1 over m here become extremely small or infinitesimal in number. Okay, then what's the implication on t? Will t be, values that are integral multiples of 1 over m? Okay, what would happen to t in this case? Then t, just imagine, if m approaches infinity, then t is 1 over infinity. And then what else? 1 over infinity, infinity, infinity. Then t itself is a continuous number, though very, very small, isn't it? Okay. So in this case, 13, okay, t becomes continuous. Okay, so that's how we link 11, which is discrete, and 13, which is continuous, because it depends on the number of compounding that you want to do. Now, when we talk about this, we cannot run away from talking about another thing, which is instantaneous rate of growth. And instantaneous rate of growth is actually the application of the issue of, continuous growth rate or continuous idea that we have here. And then later we can see how we can convert it to, discrete and vice versa. Okay, now let's talk about instantaneous rate of. Now let's look at the concept of instantaneous rate of growth. So if we can recall back the term A times E to the power of RT, okay, like I said previously, this equation is actually can be used to calculate growth, for instance, growth of money, growth of population, and other things. Yeah, so here if we look at it specifically in expression 14, we can see R here. R is actually instantaneous rate of growth of function 14. Okay, so for 14 here, how can we find the rate of change in V here? Okay, the rate of change in V is found by differentiating 14 with respect to t. So here, delta V over delta t equals to what? R A E R T, isn't it? Or we can rewrite it as what? R times V, because this one is actually equivalent to V, isn't it? Okay, so that is the rate of change. So when we talk about the rate of change, when you look at the way I did it, I use the first derivatives, differentiate 14 with respect to t. And therefore, the rate of change itself is actually the slope of V. Okay? But then from here, how can we get the rate of growth in V? Okay, the rate of growth in V is very simple. Okay, once you get this rate of change, divide this by V itself. So delta V over delta T over V. Okay, so here you can have R times V over V. What do you get? R. So the rate of growth in V is actually the R itself. Okay, now, so in this case, this is what I meant just now. Okay, the first bit here is actually the slope or the rate in change, the rate of change in V. Okay, and if you divide the rate of change in V, divide by V, then you get R. And what is R? The rate of growth in V. Okay, and the rate of growth in V here is instantaneous. Okay, at the value of R. Now, So here, the rate of growth in V, okay, is actually the rate of change in V that is expressed as a ratio to the value of V itself, isn't it? Or in other words, the rate of growth in V is actually, okay, the rate of change in V divided by V. Okay, you make sure that you can understand the rate of change is not the same as the rate of growth. Yeah, the rate of change is actually the slope. The rate of growth is the growth itself. Okay, the slope divided by the value of the function. Okay, now here we did you find the rate of growth here using a e to the power of r t. Okay, now from this equation here, a times e to the power of rt, it leads to r answer of the rate of growth in v. And the original function here, y equal to this, is actually continuous function. How do we know? Because if we look at the previous example, okay, we can see that saving is compounded continuously. I'll show you more. Yeah? So here we have the concept of continuous versus discrete growth. Okay. So what's the difference between continuous and discrete growth? So let's say we have, the first example here. Let's say pound sterling here, week here. So this is the first week. This is 0 week, second week, the third week, and so on and so forth. So let's say a child is given 5 quid allowance every week. So in the first week he received 5. In the second week he received another 5, so the total become 10 for instance, or let's say he received 10 in the following week, and so on and so forth. But you can see here, between week 1 and week 2, between week 2 and week 3, no allowances received by this child. So that's why 5 quid allowance here is actually, the growth is nothing, so it is called discrete. Okay, what about B here? If we have size and then we have this here, okay, the first 10 days, the second 10 days, and so on and so forth. Okay, so the first 10 days like this, the second 10 days is like this, but then between these 10 days, the bacteria growing, non-stop. Okay, the bacteria growing non-stop. So here is an example of continuous growth in bacteria size, isn't it? So that's the difference between continuous versus discrete growth. But this is just non-economic example. What if we look at the economic example? Okay, to differentiate between continuous and discrete growth. Alright, if we look at A here, V equals to A times E to the power of RT. Let's say we use this example, 1000 times E to the power of R, interest rate 0.06, and then compounded how many times? 5. What's the answer? If you press your calculator, then you get this, 13949.8588. What about B here? B is a different way of calculating the growth spending, isn't it? If you keep 1000 today, okay, and then interest rate is this 0.06 for 5 years, what do you get here? 1338 to 55 to 255. So you can see the first one is bigger than the second one, isn't it? Because the first one, interest rate is compounded non-stop. And in the second one, interest rate is only calculated at the end of every, period. of compounding. Alright, so obviously this one is continuous and this one is discrete. Now, you can see the difference between continuous and discrete, growth now, growth function. So A is continuous growth function, B is discrete growth function. Is there any possibility to transform the discrete growth function to continuous? Is it possible or not? So this is the thing that we want to look at now. Let's say we have the discrete compounded interest in this following sequence, yeah? So I'm sure you have seen this before, and it's very obvious it is a discrete, function. Okay, so if you look at these discrete functions here, you look at I here, what does it mean by this I? Okay, and you see the exponent here, 2, 3, and here of course 1. What's the function of exponent numbers in this case? And if you see here, we have I written in such a way that it's written as 1 plus I. How do we call this? And if we are very good enough, you can see that the pattern of writing this discrete function, okay, let me rewrite it again here. A 1 plus I to the power of whatever number, let's say 2 or 3, okay. Isn't it similar to A times B to the power of T? Isn't it? Okay. Now, what is I in this case? It is effective interest rate. What's the function of exponent numbers in this case? It basically refers to number of periods covered in compounding process. So, like I've showed you just now, that A times 1 plus I to the power of, let's say, 3 or 2 or 4 is actually the same as A times B to the power of T in terms of, construction, isn't it? So, in terms of construction, it looks more or less the same. So, is it possible, okay, to summarize this exponential function as this? Yes, isn't it? So, if that is the case, is it possible to transform this, discrete compounding of interest function into a natural exponential function? Natural exponential function means in that exponential function, okay, the base is E. Okay, is it possible or not? Okay, so here basically we're actually trying to transform discrete growth function of interest rate to a continuous one. But the question is it possible or not? So let's try. So if you look at this function here, this one, yeah, okay, in this function we have 1 plus I, isn't it? Now 1 plus I here is very obvious that it is the base of the function. That means it is B, isn't it? If you try to compare it with this one, it is B. B equals to 1 plus I. So T here in this case is what? Is the exponent of the expression of 1 plus I. And in this specific example is 3, isn't it? So T here is the exponents. Okay? But you have to remember that although we try to compare it with T here in the second function here, T here has to be discrete. Because this one is discrete, T here has to be integers only. Okay? Now, look back at B here. The term B is actually positive number, yeah? So that, if B is positive number, let's say I is negative, so I plus 1 is still positive. Okay, so in particular, this is what I mean. B equals to 1 plus I. It has to be greater than 0, positive, isn't it? Okay, so B, if we restrict it to a positive number, the base, yeah, that means we can express this B in such a way that this B is equal to any kind of real number as long as it is greater than 1 to the power of something, power of whatever. Okay, So because b can be any real number greater than 1 to the power of something, b can include e, isn't it? Natural number. So if that real number for b is natural number e, then we can rewrite it as what? We can rewrite this, okay, as this. 1 plus I is actually equal to b, isn't it? Equals to e to the power of t. Okay, so remember what did I say to you just now? If we restrict b to a positive number, that means we can express b such that b itself is equal to any real number greater than 1 to the power of something. Any real number. So any real number could be e to the power of something to the power of t. Okay? So here what we can see is that we say that we have 1 plus I to the power of t, okay, is actually equal to a times b to the power of t. Okay, a here is the principal amount. Now let's say a here is 1 quid. Okay, a here is 1 quid. So that means we can actually transform ab to the power of t into natural exponential function. Okay, but how does it look like then if we are able to transform it? So it should look like this. A times 1 plus I to the power of t equals to a times b to the power of t equals to what? E to the power of r times t. Okay. But before I forget, I think I make mistake here. It's not e to the power of t. It is e to the power of r. Otherwise, it doesn't make sense for this answer to get a times e to the power of r t. Okay, I hope you can follow up to this point. So recall back, my main point is to transform discrete function to continuous function by using reference of this. Okay, now here in 18 we can see that a times 1 plus I is actually a times e to the power of r, and a times 1 plus I square is actually a times e to the power of 2 r, isn't it? So we have a discrete case earlier, that a times 1 plus I to the power of t, isn't it? That's what I showed you earlier. But now, because of this explanation, we may consider to work with continuous exponential function of a times e to the power of r t, because discrete function here can now be transformed into continuous using natural number. But then, why natural exponential function here is widely used in economics? Like I said earlier, because of its nature of calculation is very easy. You want to differentiate it, you almost don't do anything except copying the function itself, and then when you do maximization, minimization later, because all of this involves differentiation, the differentiation process of natural exponential function is the easiest compared to other types of exponential function. Okay, so now what you have seen is that you know that any discrete growth function can be transformed into a continuous growth function, and it can be transformed using natural exponential a natural number here. What we have seen previously are the growth, okay, positive growth. Can we have negative growth? Of course we can. It's actually the reverse of the growth that we have seen earlier. So this is basically the concept of discounting. Okay, and we want to look at negative growth. We already know that we have two different cases of growth, discrete and also continuous. Now let's look at the discrete case first. So it is represented in the form of expression of 19. V equals to A times 1 plus I to the power of T. Okay, A is the principal, V is the value in the future. Okay, T is the number of period. Okay, so if we want to know how much we need to save today in order to get V in the future, so we just need to cross multiply, okay? Because this is the question of how much is the principal that we need to save today, which is A. Okay, so we cross multiply, we get this, or we can also rewrite it in this form. Okay, now what about continuous, growth function? The continuous case is given by 21, which you have seen earlier. So we want to know how much is the principal that we need to save today so that we can receive V in the future. We just need to cross multiply or divide both sides of 21 by E to the power of RT, then we get this. As you can see here, what happened is that if we write it this way, then you can see minus R, isn't it? C goes to this one. You have minus T. Now let's look at this. What is minus R in this case? If we are here, then we want to have what's the value in the future after we save certain amount of A. Okay, and then R is basically the rate of growth, isn't it? But if it is minus R, is it the negative rate of growth? We call it rate of decay. Okay, so discounting is basically you reverse the process. You have the rate of decay. Okay, so you try to do a lot of exercises for this, for continuous and also discrete. The starting point is to do exercise from the textbook, and then you can get other exercises from the internet. Now, we are done with continuous and discrete. Now, we are still talking about exponential function, but now we want to talk about the opposite of exponential function. What's the opposite of exponential function? Okay, it is logarithms. Okay, so for instance, if we have specific number here, 3 square is equivalent to 9, isn't it? This one is y, this one is b, this one is t, isn't it? Okay, or I write it this way, y equals to b to the power of t. All right, now if b is the base, okay, y is the answer, t is the exponent. But this one can be rewritten in the log form as this. T equals to log y to the base of b, isn't it? Can you see? What have I done here is that to transform exponential function to log function. Okay? So exponential function is actually anti-logarithm. Alright? Now, because a t is equivalent to log y to the base of b, okay, mathematically speaking, we can rewrite this as this, y equals to b, substitute t as this, back into the exponential function, then we get this, b to the power of log y to the base of b, isn't it? Okay, so this is what I'm talking about. Alright, now let's go back to this function, exponential function, y equals to b to the power of t. Okay, and such that b has to be positive and greater than 1. If this is the case, then like I said previously, this exponential function is monotonically increasing, okay, or upsloping, okay, like the way we drew it earlier, if you can recall back. Okay, so we did draw this function like this earlier, isn't it? So it is monotonically increasing. All right, let's go back to our current slide. Okay, so you look here, for this generic function of exponential function, for every value of positive y here, yeah, let's say 9 or whatever value, okay, there is a unique or non-trivial value of t, isn't it? If we say that this function is monotonically increasing, okay, such that, this function gives you b positive, okay, b greater than 1 or b positive, whatever, okay, but as long as b is positive. All right, now, so that means in this case, if we have y here which is very, very large, then that means t has to be very, very large as well, isn't it? Okay. Now, from here, what can we say? The function is monotonically increasing, isn't it? And the monotonicity of exponential functions in this case implies what? Okay, so when this function y equals to b to the power of t is strictly and monotonically increasing, any positive y, in this case, must have a unique logarithm t to a base b greater than 1. So, the larger is the y, the larger is the logarithm, isn't it? Alright? And next question is, because I keep telling you y has to be positive in order to have logarithmic function, can we have instead, can we have y, negative y, to have a logarithm? What about if y is 0? Can we have a logarithm? So I want you to figure it out, whether we can have y, negative y or 0y to have a logarithm. All right. So the next thing is we want to look at the logarithmic function specifically, and also some proof of logarithmic function, formula or, calculation. All right. But then another thing that we need to emphasize here is about common log and natural log. For any logarithmic function, if you see and read a lot of maths book or mathematical economics books, then you can see there are two main log functions that are very widely used. Those are common log and also natural log. Okay, so the two numbers related to these are basically 10 for common log, 10 is the common base, and e for natural log. Okay, now let's say we have this here, log of 1000 to the base of 10 is 3. But if we write anti-log, it's actually what? It's actually 1000 equals to 10 cubed, isn't it? So this is our y equals to b to the power of t, anti-log, So, but if we have log 100 to the base of 10 equals to 2, this can be represented as the following. 100 equals to 10 square, isn't it? So t here is 2, b here is 10, and y here is 100 for anti-log function. If we have ln y equals to t, for instance, how do you write it? In the form of anti-log. And what about if you have y equals to e to the power of x? How do you write it? In logarithmic function. Okay, so here, if we have, ln y equals to t, ln y equals to t, then t here can be rewritten as what? Can be rewritten as log of y to the base of e, isn't it? Because, okay, the anti-log function here is y equals to e to the power of t, isn't it? Okay. But if we have something like this, for instance, this is the first one. The second one, ln e, natural log e cube. Okay, natural log e cube, if we try to write it in the form of log form, this is natural log, we want to write it in common log, then it becomes log e cube to the base of e, isn't it? And the answer is actually 3, isn't it? If we have the third example, for instance, let's say ln e square in the common log function, it is log e square to the base of e, then it's equals to 2, isn't it? And so on and so forth. So here, if I go further, then I can see that natural number e to the power of k, such that if k is, real number, we can therefore have, k being expressed as ln, okay, natural log of e to the power of k, isn't it? That's what we can find from here. Okay, so let's crack on. We now want to look and want to analyze different rules of logarithm so that we can do some, arithmetic operations, okay, for such functions. So what are those rules? These are the rules. Log of a product is the rule number 1, and then log of quotient, log of power, conversion of log base, and then lastly inversion of log base. For your information, when I teach you rules of logarithm here, I'll show you the example, I'll show you the main, generic form, and then the new thing that you haven't seen before is I will show you the proof of why log of a product becomes such answer or such, such results, or for instance, or why log of quotient gives you certain rule, and this rule is applicable to all. Okay, so this is a proof, and I'm sure this is something new to most of you because you didn't do Bachelor of Mathematics before you registered this module. All right, the proof is the common, knowledge learned by students that are those who are doing Bachelor of Mathematics. So now I'm going to teach you like the way lecturer teach, any lecturer teaches, Bachelor of Mathematics students. Okay, now let's look at the first rule. We call it log of a product. So the first rule is log of a product. Product in mathematics means multiply. Okay, let's look at expression 26. Let's say we have natural log of u times v. Rule of log of a product says that it is actually equivalent to natural log of u plus natural log of v. Okay, so let's look at the example first before we go into detail on the proof. As you can see here, natural log or ln e square times e cube is actually natural log of e square plus natural log of e cube. Because we can simplify it further, you don't leave it just like that, the natural log of e square is actually 2. Natural log of e cube is actually 3. So it becomes 2 plus 3 equals to 5. That's the final answer. As long as you can simplify it, don't leave it just like that. Okay, now let's look at second example. Natural log of q times e to the power of 5 is actually equivalent to natural log of q plus natural log of e to the power of 5. Now, natural log of q, we cannot simplify it further. But then, natural log of e to the power of 5, we can simplify it and it becomes 5. So this is the final answer. Okay, now let's look at the proof. Okay, let's say we have two terms. Okay, u and v. Okay, u and v. In Greek letter is me and nu. Okay, so if we have ln u, ln u is, defined as the power to which e must be raised to attain the value of u. Okay? Ln u or natural log of u is the power, to which e must be raised to attain the value of u. Now, this means, okay, if we have, e must be raised to a power. What is that power? Ln u or natural log u. This is what it means. And it is what? It is u. Okay, this is what it means. Similarly, okay, if we have, let's say, a, okay, e to the power of ln v, then it becomes equals to v, isn't it? Okay. And this also implies if we have e to the power of ln u times v, okay, then it's equal to u times v, isn't it? Okay, that's for b. And if you look at b here, it is actually the exponential expression for uv, isn't it? Okay. But then for b here, okay, I mean for uv, we can also have another way to write uv. Okay. What is that another way to write uv? Another way to write uv is that by having a direct multiplication of u and v. Okay, so I'm talking about C. A direct multiplication of u and v means u times v is actually what? We already know that u is equivalent to e to the power of ln u. We also know that v is actually e to the power of ln v. Okay, then we can substitute it back into C here. Then we can have what? E to the power of ln u times e to the power of ln v, isn't it? Okay. Because they have the same base, so the power here, mathematically speaking, we can plus them, isn't it? Therefore, we can rewrite C as e to the power of ln u plus ln v, isn't it? Is it clear? Now you look here, we now equate b and c, okay? Then b and c can be equated because both of them are uv. So because I don't have enough space here, let me bring it here. Okay. So uv is actually what? It's actually from b itself is e to the power of ln uv, isn't it? I put bracket here so that you're not confused. And if it is from C, let me write it properly. If it is from C, it is actually E, okay, to the power of ln U plus ln V, isn't it? Okay. Now, E on the base is just the same, and the power is also the same. Therefore, this implies ln uv is actually equivalent to ln u plus ln v. Okay, ln u plus ln v. Okay, QED. That's how we prove it. QED means it has been proven in Italian language, Latin language. Sorry. So I have shown you how to prove, but I didn't write full sentence. So when you prove, you need to write full sentences of proving. Yeah. What are the full sentences of proving? Whatever I said to you just now, in order to prove the log of product is like this. Okay. So whatever I write here is not sufficient. You have to write whatever I say also, then the proof is complete. Okay. Now, once you finish proving like what I did just now, you can put QED. But if you type it using computer, usually they use this symbol, square symbol or darken square symbol. If you want to see this in applications, you can see a lot of this in economic journal articles for theoretical papers. All right. In mathematical economics, in the study of economics, when you prove using mathematics like this, you need to write sentences in between here. If you just write like the way I write here without writing whatever I said just now, then nobody can understand your proof. You have to put in the middle. For instance, here, C here is another way to write UV. That is a direct multiplication of U times V, isn't it? Then we can rewrite it by having this from A, by having this, okay, from A also, from the concept that we explained in A, then we can write it this way because, when you have the same base, then the power can just easily be added to each other. Okay, then finally we get to the final stage here. Okay, for clearer explanation in terms of writing sentences, you need to read textbooks so that you can understand more. Whenever you study mathematical economics, it's not sufficient just to refer to the slides and also the video. You must read the textbook so that you can become familiar with the mathematical languages used in the textbook. Because those mathematical mathematical language, yeah, mathematical language used in the textbook is the formal mathematics language that is used to explain economic theories and also other theories that use, mathematics as the method. Okay. Let's move to the second rule. The second rule is what we call rule of quotient. If we look at the rule of quotient, quotient itself is actually a ratio. So let's say we have expression 27 here. Ln u over v is actually can be rewritten as ln u minus ln v, such that u and v are positive. Let's look at the example here. We have ln e to the power of t divided by c. Ln e to the power of t divided by c can be rewritten as ln e to the power of t minus ln c, isn't it? Can we simplify it further? Of course. This one yes, this one no. Then it becomes t minus ln c. That's it. What about the second one here? Ln e to the power of t divided by ey. Then we can have ln e to the power of t minus ln e to the power of y. Can we simplify further? Yes. Both of these can be simplified further. So it becomes t minus y. That's it. Very simple, isn't it? Now, next come the proof. How to prove log of quotient? The proof of rule number 2 here is just very similar to rule number 1, except that now we are talking about division instead of multiplication. So I want you to try it on your own and then compare it with the textbook, the proof in the textbook. You should try because in this module, I may ask you how to prove certain, rules, theorems, and also other things. Please do the exercises on the proof as well. Let's continue with another rule of logarithm. So here we have what we call log of a power rule. If you look at expression 28 here, log of a power rule says that natural log u to the power of a can be rewritten as a times natural log u, such that u is greater than 0 or u is positive. Okay, before we go to the proof, let's look at some numerical example. For instance, a. Natural log of e to the power of 10 this actually can be rewritten as 10 times natural log of e and can be simplified further equals to 10. If we have b, natural log of q square can be rewritten as 2 times natural log of q, but then we cannot simplify it further because we don't know the value of q. Okay. What about natural log q times w to the power of a? Can you do it yourself? Because now it is very simple. Now let's move to the proof. How the left hand side here can be equal to the right hand side. How the log of a power can be rewritten as this way. Okay, so you listen to what I say one by one here, and then you need to jot down what I say so that it becomes a complete proof. What I write on the slide here are just simplification, but it's not complete. Okay, so let's say by definition, okay, let's say we have e to the power of natural log u. Okay, now if we have e to the power of natural log u, you have seen this in the rule number 1 proof, isn't it? So this one can be rewritten as u, isn't it, or me? Okay, in Greek letter it's actually me. And also if we have b, okay, let's say we have e to the power of natural log u to the power of a, okay, this one can be rewritten as u to the power of a, isn't it? Okay, so we have two different expressions here, but the concept is just the same, isn't it? Now you look at b here, okay, u or me to the power of a, u or me to the power of a. If you say it in Greek letter, we call it me, but if you say it in, English letter, we call it, Latin letter, we call it u. Okay, now anyway, so if you say u to the power of a, okay, so we have u to the power of a, u to the power of a, instead of writing it as b, we can also have it in another different types of expression. We call it c, for instance, yeah? Okay, so u to the power of a is actually can be written as, okay, e to the power of ln or natural log u or me. Why? Because u here, as you can see, is actually defined as the one in a, isn't it? So you can see e to the power of natural log of u. Okay? And then to the power of a, then the whole thing of u here is to the power of a. Can you see? Okay? So this is actually u from a. Okay? This is the power, that's all. Okay? And from here, we can also rewrite and simplify it further to e to the power of, because this is power, you look at the exponent here, exponent power, isn't it? So when it is power, we can multiply. So when we can multiply, it becomes e to the power of a times natural log of me or you. You get me? Okay, so you see here, e in c here is equal to e on the right hand side of c, isn't it? Therefore, the natural log expression here on the power on the exponent here is actually the same as this. Okay, so from here, from c, we can have ln u to the power of a is actually equivalent to a ln u. Okay, so can you see this one is similar to this? So QED, it has been proven. Okay, is it clear? Try to look at more examples, yeah, for exercise in, textbook and also on the internet. Then it give you a clear idea. And try to practice as much as you can, okay, for writing the proof here. Then you can, get some idea of writing the proof. Not all the things I'll prove in, this module, but at least for the starting point, I'll teach you how to do proving. Okay. In fact, for Bachelor of Mathematics students, they have one module specifically studying for proving. And proving is very important in the study of economics. Why? Because if you want to say, one economic variable on the left-hand side here can be shown in the form of another way of writing it, but and this another way can give you variety ways of interpretation using different types of economic intuition. Okay, then you have to prove it that it can be done that way, so that after you prove it, then this kind of interpretation can be used to explain more economic intuition in the future, and it becomes more useful for economists. Before it becomes more useful to economists, you have to prove it. That's why you need to learn proving also, even if you're not mathematics students. Okay, now let's crack on. So here what you can see, we have done three different rules of logarithm. So we can see that these three different rules, okay, rule number 1, 2, and 3, can actually help or facilitate us in simplifying the mathematical operation in certain types of problem, isn't it? Okay, so if you see A here, which rule, yeah, because we have rule number 1, 2, and 3, which rule can facilitate us, okay, uh, in terms of multiplication operation into an additive one, okay, division into subtraction, reduce the power to multiplicative constant. So this one is usually rule 1, okay, can help us. If you see logarithm is in the form of multiplication, you can change it to additive one. If you see it in the form of division, okay, we can have subtraction. This is referring to rule number 2, and this one is referring to rule number 3. Okay, so we are done with 3 rules, but we haven't finished all the rules here. Now let's move to the next rule, rule number 4. And rule number 4 here is what we call conversion of log base. So conversion of log base here, if you look at the expression 29, it says what? Log of u to the base of b is actually can be rewritten as the right hand side here. Specifically, the right hand side shows you what? Log of natural number e to the base of b multiplied by log of u to the base of e, or natural number, such that u has to be positive. Okay, if u is not positive, then it leads to certain problem and we cannot use this conversion of log base rule. Okay, now, so here if you see this rule properly, you can see that it resembles the chain rule. Now, how it resembles the chain rule? If you look at it carefully, okay, you can see the chain from B to E, E to E, and then E to U. Okay, so that's why it is called chain rule. So B to E, and then E to E, and then E to U. Okay, and here it resembles, chain rule, and therefore this rule basically allows us to derive a logarithm of log u to the base of e from the logarithm of log u to the base of b, and vice versa. Okay, so let's look at the proof, and this proof is a little bit, tricky if you don't know how to understand it mathematically, but in fact it is very, very easy. Now, you look here. So let's say we have u, or me, and u is rewritten as e to the power of, rho. Okay, this is rho, the way I write it. It looks like p, but it's actually rho. Okay, so let's say we have this expression. So from here, if we want to write rho can be rewritten as log u to the base of natural number e, isn't it? So that rho is actually log u to the base of e. Okay, so from here, from this, it follows that, okay, so from here, it follows that we can have something like this. Now, look at this carefully, yeah? So, let me put it here because I want to have more space. So, we can have something like this. So, log u to the base of b can actually be rewritten as, look here. You look at the base, I log to the base of b. But what is u? You see u that we have defined just now? So we replace this u, substitute it by e to the power of rho here, yeah? E to the power of rho. That's why, you need to have definition. Otherwise, you cannot just easily substitute it back here. Okay? And then, after that, you look at this. Okay? This, remember, this is log e to the power of rho to the base of b. And you see natural number, isn't it? Therefore, you see the power here? You can bring it to the left because of, rule of multiplication, isn't it? Okay, so rho times what? Times log e to the base of b. Can you see? Because we have power here, the power is rho, we bring it to the left side of log b. We can rewritten it this way. Okay, I hope up to this point you understand. Now next, okay, we have this. Okay, look at this, rho. Rho is equal to what? Rho is equal to log u to the base of e. Substitute it back into this expression. So log u to the base of e. Okay, times what? Times this second expression. Log e to the base of b. Okay, now recall back, we want to prove that this one has to be equal to this. This one is actually this, isn't it? Now, this one is actually what? This one is actually this, isn't it? It's just that the location is, the location is different. You just can easily interchange it. Okay? So, it has been proven. Of course, your teacher, the way I explained to you looks so simple, but you need to do a lot of exercises so that you can gauge some idea on how to do proof. Yeah? Okay. Now, so let me erase some mess here so that I can, you can see clearly the next explanation about this. Okay. So here, if you look at expression 29, has been proven by this. Okay. So here, we use natural number e. And we know that natural number e is actually a constant, 2.7 something, isn't it? But is it possible to have this kind of conversion of log base using other types of constant other than e? Yes. So that means we can also generalize rule number 4, isn't it? So if we generalize rule number 4, it becomes 30 here. So you see log u to the base of b is actually the multiplication of these two log. The first one is log c to the base of b times log u to the base of c. So you see c here is constant number. It can be e, it can be other number as long as c here is the same as c here. Okay, so here in 30, c is some base other than b, but it can't be the same as b, yeah? Alright, so that is a rule number 4. Now, let's move to the last rule. And the last rule is rule number 5, inversion of log base, inverse. Okay, so inversion of log base is very simple. You look at expression 31. Log e to the base of b is actually the reciprocal of log b to the base of e. That's it. Okay, now how to prove it? Okay, so here the proof is written here. Now, you look at this proof, recall back we have rule number 4. Rule number 4 states that log u to the base of p is actually the multiplication of log e to the base of p times log u to the base of e based on chain. Isn't it? It looks like a chain. Such that u is positive. Okay, so from here, let's say u itself is the same as the base, okay, b. Therefore, because u is the same as the base, b, then we can rewrite 29 and substitute u, you use b instead. So here, u here becomes b. U here also becomes b. So when we substitute it, it becomes 30. So log b to the base of b equals to multiplication of log e to the base of b times log b to the base of e. But we already know that log b to the base of b, or log that a number to the base of itself, is actually 1. Okay, so because the left hand side here is 1, if you cross multiply it, then you can get, something like 31 here. So that's why it says here this log e to the base of b and log b to the base of e must be reciprocal to each other. So that means from 30 here, what I mean here is that you cross multiply, okay, log e to the base of b. So you get log e to the base of b, you can get log b to the base of e, isn't it? Or you cross multiply in a different way, you can also get something like this. Log b to the base of e equals to log e to the base of b. And this one is actually the same as this, isn't it? Okay, so that's why it says must be reciprocal to each other, QET. Or you can put this, empty square, or you can put this full square to see that it has been proven. All right, that's all for the proof of logarithm, but there are a lot of proof I won't cover here, but at least you get some idea of how to do proving in mathematical economics. Okay, so the idea here is that every time you introduce new rule, there must be a proof. Okay, so without proof, at least one proof, without proof, then the rule is not, it's not strong, it's not valid. All right. So here we have seen different types of rules for logarithmic function. And the purpose of having all of these kinds of rules is to help us in simplifying the calculations, especially when it comes to exponential functions. So let's look at example here on how it can be used to simplifying the calculation. So let's look here at the expression 31. In the expression 31 here, as you can see, beta phi to the power of x minus me equals to 0. So this is actually when it's equals to 0, that means beta phi to the power of x is actually equals to me, isn't it? So this is one example of equilibrium condition actually. All right now. So here, from here we can rewrite it as this, beta phi to the power of x equals to me, in it. Okay. Now, the next thing that we need to do is that, let's say we need to find x, and this is the question. What do we need to do? Actually, okay, in order to find x here, if you look at this equation here, I call it 31a for instance. This equation is nonlinear equation because you can see x is in the form of exponent multiplied by some other terms or coefficients. Then you know that it is nonlinear. Okay, but let's say beta is one variable, phi, and then also me is are also another different types of variable. So you collect data for beta. Let's say beta is GDP per capita. Phi is, let's say, education level. Me is, let's say, which earned by labor. Yeah. Then how to find x here? For instance, let's say x here is the elasticity of educations. I'm just making up, yeah. So in this case, if it is non-linear like this, it's not easy to solve actually. So what we can do is that we can transform 31a into log function. Okay, so if we transform it into log function, then we can have, all right. So log beta plus log phi to the power of x equals to log me, isn't it? Can we simplify it further? You have to write some sentences here, yeah? If you just say from here to here without saying some sentences, I don't know what you're doing. So basically from here to here, we are transforming the expression 31a into log form. And we can simplify it even further because this one can be rewritten as, so x log phi plus log beta equals to log me, isn't it? So from here, mathematically speaking, x log phi equals to log me minus log beta, isn't it? So from here, because I don't have enough space, so I write it here. So x is actually, remember we need to find x, so that's the objective. X is actually log me minus log beta divided by log phi. So that's how you find x. So if you know what is the me value, you know what is beta value, you know what is alpha, data collected, then x here is in the form of linear function of all of this me, beta, and phi. Okay. Now, so don't forget to do exercises in the textbook, because this can, give you a better idea about what you have learned in this lecture. Now, we move to logarithmic functions specifically. So here are the examples. If you look at the first example, t equivalent to, or t equals to log y to the base of b. So here the case base here is b, isn't it? So second one here is that t equals to log y to the base of e. Then log y to the base of e is actually, natural log of y. So what's the difference between a and b? The base is different, yeah? Because the base in the second one here is, the base is a natural number. Okay? Now, if we have log functions here, and we want to look at it as the inverse, then we can have exponential function, remember? Because anti-log is actually exponential function, isn't it? So log functions, in other words, are an inverse of exponential function. Okay, so here we want to put it in the form of graph. So let's say we have exponential function y equals to b to the power of t. Okay, but then we want to make it, specific exponential function. The base here p is actually natural number, y equals to e to the power of t. Okay, instead, this is very general, so we make it specific, y equals to e to the power of t. Now, if we want to put this function in the form of graph, this is an exponential function, specifically natural number for exponential function. So let's say we put y on the vertical axis and t on the horizontal axis, because here in the graph y depends on t in it, and we can have division of this first quadrant, yeah, and equal division. Therefore here is actually 45 degree in it. Okay, now if we try to put this in the form of diagram, then you know that when t is 0, y is equivalent to 1, isn't it? So when you draw it, then you can get something like this. So here is y equals to e to the power of t. Okay, but then just imagine, yeah, if we have y equals to e to the power of t, if you take it in the form, transform it in the log form, okay, then you can have what? T equals to log y to the base of e, isn't it? So this one is transformed into log form, that becomes this. So now t depends on y, okay, not y depends on t. So if I put the graph here, okay, another one here, so I put y here and then t here instead, then I divide the graph into two equal area, then I can have here 45 degree. Then if I draw it in this second graph here, what happens is that, let's call this graph A, this one graph B. Then what happens is that, okay, let's say y is 0, then let's say y is 1. Okay, let's say y is 1. What happens to t? T becomes 0. So here, when we draw it, we get something like this, isn't it? So this one is t equals to log y to the base of e. As you can see here, a and b, what's the difference? A is exponential function, but b is a transformation of exponential function into log form. And you can see that a is above the dash line, and graph B, the curve is below the dash line. And also, if that means A, when you flip it with this, over the dash line here, it becomes B, isn't it? Okay, so From these two graphs, actually, we have several implications of exponential function being transformed into log function and vice versa. So what are the several implications of drawing when we have exponential function as compared to, log functions and vice versa? Now, we have several implications here. So the first one is that when you see graph A, you can see that, okay, y is y is actually increasing at increasing rate, isn't it? Because it is convex. Okay, y is increasing at increasing rate. So let's say I use a red pen here. So that means, how do I know it is at increasing rate? You look at the nature of the slope. The first slope is here, the second slope is here, the third slope is here. What happens to the slope? Slope is increasing, isn't it? At what rate? At increasing rate, because it becomes steeper and steeper. But if you look here, second graph, when it is transformed into log form, slope here looks like this, and then here looks like this. It's still increasing because the curve is upsloping. Both of the curves, A and B, are upsloping, but then in B you can see the slope becomes flatter and flatter. What does it mean? It is increasing but at decreasing rate. So that means if you have exponential function in A, when you transform it to log form, then the slope still increases but at decreasing rate. Okay? So we have the opposite rate of increasing here between A and B. And if you look at A here, in this case, y as a function of e to the power of t, you must recognize which one is domain, which one is range. Which one is domain in the first graph here? T is domain, isn't it? All values of t is permissible values of t. What is the range? The range is all value of y in the set of y. I mean the permissible value of y. You can see y here, regardless what happens to t, whether, either negative or, positive value of t, you can see y is always positive and never touches this horizontal line. Yeah? I did mention about this concept last time. So we have positive range values or y values here. But in the second graph here, as you can see, for this log function, okay, what happens here is that recognize first which one is domain, which one is range. Domain is y, range is t. As you can see here, what happens is that domain is always positive, isn't it? Regardless what happens to t. T here, if you pick this point, t here is negative, but y here is positive, you get me? If you pick this point also, t here is negative, but y here is positive. If you pick this point, t is positive, y is positive. So, regardless what happens to t values, we can always have positive values for domain, that is y in the second graph. Okay, and the last implication that we can see, like actually I did mention to you earlier, you look at the first graph, it is an exponential function, it is upsloping and increasing rate. When you flip it, over this dashed line, then you can have graph B. Okay, that means, exponential function and also log function, when it is transformed into log function is actually the mirror reflection of exponential function. Okay, so these are the implications of, inversing, exponential function to log function and vice versa. All right, now we are done with this. Now we want to look at the base conversion. We want to derive the formula of base conversion, and this is not difficult to understand actually. So we know that we can always convert any exponential function. Let's say this function is exponential function, isn't it? Y equals to AB to the power of t, yeah? To natural exponential function to, okay, y equals to AE to the power of RT. So we can always inverse them. So how to do this? Now we need to utilize certain things. you want to convert A, okay, B to the power of T here, isn't it? And T here, the expanding or contraction factor is 1. So, or you can put C here. So, we want to convert general form of exponential function, which is A times B to the power of Ct into A times E to the power of Rt. You look here, A here equals to A here, okay? Then T here equals to T here. That means if we want to convert, we must make sure that B to the power of C must be equal to E to the power of R, isn't it? Because A is already equals to this, T equals to T here, isn't it? So the only things that are not the same is B to the power of C and also E to the power of R. But in order to convert, that means B to the power of C must be equal to E to the power of R, isn't it? Okay, so here the main point is to find the R value from the given value of B and C such that these two holds. Expression 32 holds. So how to find, R values from 32? Can we get the solution here? So here, let me erase some so that it won't be a mess. Okay, so here, let me erase this first. I need some space. All right. Okay, so we want to convert A times B to the power of Ct, convert it to A times E to the power of Rt. Okay, I did mention to you A here equals to A here, T here equals to T here. Then we have to make sure that we need to find R for a given value of B and E. Okay, B and C, B and C here, such that E to the power of R equals to B to the power of C. Okay, so how to find this basically? Then the easiest way is to convert it, to transform it to natural log first. So transform this expression 32 into natural log. Okay, then we can have what we call ln B to the power of C equals to ln E to the power of R in it. And then this can be rewritten as C ln B equals to R ln E, isn't it? Do you remember this rule? Okay. Now, so here, once we have this, we can always find the value. Okay, it's very simple already. Now, here, if we look at the example, okay, look at the example here. I pick one example only, the rest you should try it. So here, before you go to example here, so when we have, I need to finish this, y equals to a times b to the power of ct, okay, therefore can be rewritten as, okay, recall back from here, we have what? We have c ln b equals to r ln e, isn't it? Alright, now from here, y equals to 8 times b to the power of ct can be rewritten as, because you recall back, y equals to a e, okay, rt. We want to transform this to this, isn't it? So when you want to transform it, a stay the same, isn't it? So we can have y equals to a, because a the same as a in the second one here, okay, and then b we transform it to e, okay, because we want to transform any function to natural exponential function. Remember, that's our objective, e, okay, and then t stay the same, isn't it? Because t here stay the same as t. But what about c? C has to be the same as r, but how can we make it? Because we have done it earlier. As you can see here, all right, we need to substitute this, okay, back into this so that we can rewrite it this way. A times e to the power of c ln b. That's it. Okay, so you substitute. Now let's look at the example here. Y equals to 2 to the power of t. Convert the following to the natural exponential function. Okay, so in this case, you can see, detect first which one is A, B, C. A equals to 1, isn't it? B equals to 2, and C here equals to 1, because you don't see C after T. That means C equals to 1. So from here, R is actually, we know that R is actually C ln B. Okay. Therefore, when C is 1, 1 ln B ln 2 equals to 2, isn't it? 1 times ln 2, 1 natural log 2. So, exponential function becomes like this. Y equals to A times e to the power of RT, isn't it? A is 1, E is E, R is actually ln 2, and then times T. So, simplify further. E to the power of ln 2 times t, isn't it? So that's our exponential function. Why don't you try the rest of it? Try to come up with exponential function, but you need to determine which one is A, B, and C. Okay? And now, before I forget, we need to go back to this actually. All right, let's go back to this. So when I say, the second graph here is a mirror reflection of the first one, then we can have certain summary here. So what I mean by certain summary here is that, let me erase some space so that I can write some summary here. Okay, what I mean here is that you can see when y is between 0 and 1, okay, log y is less than 0, isn't it? All right. So you can see here when y is between 0 and 1, log y is less than 0, negative. In order to understand this, you must refer to second graph here. Let me erase some mess. All right. So you can see here, 1 is here, isn't it? So 1 is here. Anything less than 1 between 0 and 1 is here, isn't it? So y between 0 and 1 is here. You can see that log is negative, less than y. This is what it means. Also, when y equals to 1, okay, this implies that log y equals to 0, isn't it? This point. When y equals to 1, log y is 0, isn't it? Look at graph B. Okay. When y is positive, then what happens to log y? Log y is also positive. You look here. Okay. So this implies this. So here, let me write it properly. Yeah. So when this happens, this implies this. We don't say this equal to this. When I have sign error like this on the left hand side and also the right hand side, it means this one implies this, yeah? Or this one also implies this. Okay? Now, the next thing that we need to realize is that, as you can see, okay, you can see that when log y approaches infinity, okay, log y approaches infinity as what here? As y also approaches infinity. Log y approaches minus infinity as y approaches 0, isn't it? Okay, this is what I mean just now. Let me write it properly because I don't think you can understand my writing here. So here, this is what I mean. This is the second summary. Yeah? So here, log y approaches infinity, okay, as y approaches infinity, okay. Log y approaches minus infinity as y approaches 0 from right side, okay. So here, okay, and here. All right, now let's look at the graph here so that you can understand what does it mean. Okay, so here, when y approaches infinity, you look here, y is on the horizontal axis, okay. Log y approaches infinity. When y approaches infinity means y becomes larger and larger. What happens to log y here? Log y, increase, keeps continuing, y also, log y also infinity. But then, you look here, as y approaches 0 from from right hand side, this is right hand side, yeah? Right hand side move to the left, then y becomes, approaching to 0, isn't it? What happens to log y? Log y becomes negative. This is how we read it. All of this summary can be found in the textbook. All right. So that's it for this topic, this logarithm and also exponential function topic. Please do a lot of exercises in order for you to understand more about this topic and try to learn more about how to do proof. Yeah, I already taught you how to do proof in the previous section where we talk about the rule of logarithm. Please do some proof. You can get some exercises from textbook and also from the internet on the proof. I'm not going to say that you need to study all different types of proof as the way students who are learning Bachelor of Mathematics doing proof. No, but at least you have some basic idea and knowledge on how to do basic proof. So thank you.